Module 3, Section 2.5, Exponential Functions. Objectives. Objective 1. Graph and identify the properties of exponential functions. Objective 2. Solve exponential equations. Objective 3. Solve exponential equations using graphing calculator. Objective 4. Graph and identify the properties of natural exponential functions. And Objective 5. Application problems, compound interest. Objective 1. Exponential functions. We start by noting that f of x equal to 2 power x and g of x equal to x square are not the same function. The function g is a quadratic function and the function f is an exponential function. An exponential function is a function of the form f of x equal to b power x, where b is greater than 0, b not equal to 1, and x is a real number. The number b is called the base of the function. The domain of f is the set of all real numbers, and the range is the set of all positive reals. Examples: f of x equal to 3 power x and f of x equal to 1 by 2 power x are examples of exponential functions. We require the base b to be positive to avoid imaginary numbers, and we exclude b equal to 1 as a base because f of x equal to 1 power x is the same as 1, which is a constant function. Here is a riddle for your enjoyment. Suppose you received a penny on the first day of December, 2 pennies on the second day of December, 4 pennies on the third day, 8 pennies on the fourth day, and so on. How much money would you receive on December 31st if this pattern of payment continues? Here is a solution for you to look at. You'll be surprised to know that this amount will be a huge number. The above example shows how an exponential function grows extremely rapidly. In this case, the exponential function f of x equal to 2 power x is used to model this problem. Here is how the graph of y equal to 2 power x will look like. It passes through the point 0, 1, and it increases very rapidly. If we graph the function f of x equal to 1 by 2 power x, which can also be written as 2 power negative x, the graph will look like this. The graph again passes through the point 0, 1. The domain is all real numbers, and we can notice that the graph is decreasing from left to right. The graph is continuous, and we have a list of other properties here. The graph of y equal to 1 by 2 power x, which is also equal to 2 power negative x, is the same as the graph of f of x equal to 2 power x reflected about the y-axis. So that means the graph of y equal to 2 power x will be looking like this. Here are some other examples of exponential graphs. We have the formula f of x equal to 4 power negative x. Graph will be a decreasing function. It is a reflection of the graph of f of x equal to 4 power x about the y-axis, and it passes through the point 0, 1. Some basic properties of the graph of f of x equal to b power x, where b is greater than 0 and b not equal to 1. All graphs will pass through the point 0, 1. And all graphs are continuous curves with no holes or jumps. The x-axis is a horizontal asymptote, and if b is greater than 1, then b power x increases as x increases. And also notice that if b is between 0 and 1, then b power x will be decreasing as x increases. Let's do an example. Graph the function y equal to 3 power x using a graphing calculator over the interval negative 2 to 2. We enter the formula y equal to 3 power x and select a window negative 2 to 2 for x and negative 10 to 10 for y with a y scale equal to 1. If you press graph, you'll get a shape of the graph. Here is a comparison of graphs of some exponential functions with base greater than 1. We have 3 exponential functions here with the base 2, base 3, and base 4. When the base is greater than 1, as x increases, the function also increases. Notice that the larger the base, the faster the function will increase, which means that the curve gets steeper as the base increases. Here we compare graphs of exponential functions with base lying between 0 and 1. We have 4 graphs here with base equal to 1 by 2, 1 by 3, 1 by 4 and 1 by 5. Again, notice that all these graphs are passing through 0, 1. The smaller the base, the faster the function will decrease, which means that the curve gets steeper as the base decreases. Here are some properties of exponential functions. And we are going to use property 2 and 3 for solving some exponential equations. This means that if a power x equal to a power y, then we can equate the exponents x and y. That means if the bases are equal, then the exponents will be equal. And here we are saying that if the exponents are equal, then the bases will be equal. Objective 3. Solve exponential equations. Here is a procedure to solve an exponential equation. 1. Get the same base on both sides of the equation if possible. Equate the exponents of each side of the equation. Then solve the equation from step 2. Solve the given equation for x. 5 to the power negative 4x minus 5 equal to 125. Notice that 125 is the same as 5 to the power 3. So we get the bases equal. So I can actually equate the exponents. So this equation implies that negative 4x negative 5, which is the exponent here on the left side, equal to the exponent on the right side. So if I divide with the negative 4, I will get x equal to negative 2. So this is going to be the solution. In the next example, we are getting 4 to the power negative 3x negative x square equal to 4 to the power 2. Here the bases are 4, they are equal. So I can equate the exponents. This exponent here is equal to exponent on the right. What does that equation mean? That equation means negative 3x negative x square equal to 2. If we simplify this, I can write it as x square plus 3x plus 2 equal to 0. So this is factorable. X plus 2 multiplied with x plus 1 equal to 0. So x plus 2 equal to 0 or x plus 1 equal to 0. So that gives the two x values, x equal to negative 2 or x equal to negative 1. Objective 3. Solve exponential equations using graphing calculator. Here is a procedure. We take y1 as the left side of the equation and y2 as the right side of the equation. Now if we graph these two curves and find the point of intersection, we can say that the x-coordinate of the point of intersection is the solution. Here is a demonstration of that. Solve for x using calculator over the interval negative 2 to 2. The equation is 4 to the power 4x equal to 4 to the power 1 minus 2x. What we need to do is we need to graph these two functions, y1 equal to 4 to the power 4x, which is the left hand side, and y2 equal to 4 to the power 1 minus 2x, which is the right hand side function. We can select a window, negative 2 to 2 and negative 10 to 10. If we find the point of intersection, we will get 0.1667 rounded to 4 decimals. So this will be the answer. Objective 4. Basic exponential functions. Of all the possible bases b we can use for the exponential function y equal to b power x, probably the most useful one is the exponential function with base e. The base e is an irrational number and like pi cannot be represented exactly by any finite decimal fraction. However, e can be approximated as closely as we like by evaluating the expression 1 plus 1 by x to the power x with the x taken very large. Here is a table of values that is used to approximate the base e. So notice that when x is very large, this 1 plus 1 by x to the power x is coming closer and closer to this number 2.718 or 69 and so on. So this can be taken as an approximation for e. Exponential function with the base e. This is how the graph of y equal to e power x and y equal to e power negative x will look like. And notice that the domain is all real numbers and the range is all real numbers greater than 0. We have an example here. Graph the following exponential functions using a calculator. Y equal to e to the power 3x, and the second example will be y equal to e to the power 2x plus 5. Notice that the base is e. We can enter the function like this: e to the power 3x. So we have the exponential function built in here, second ln 3 times x, close the parenthesis. Then we can use a standard window, and if we graph this, we will get the graph look like this. If we want to graph the second function, we can change the formula to exponential 2x plus 5 and graph, and we can adjust the window as we need. Solve the given equation for x. X minus 1 multiplied with e power x equal to 0. And notice that e power x is not equal to 0. So we can divide both sides by e power x. If I divide both sides by e power x, I will get x minus 1 multiplied with e power x divided with e power x will be 0 divided by e power x. That will be 0. So we get a new equation which is x minus 1 equal to 0. So that tells you that x has to be 1. So that is the solution here. Here is another example. Solve for x both graphically and algebraically. 7x e to the power negative 4x plus x square multiplied with e power negative 4x equal to 0. If you are doing this algebraically, we can take a common factor e power negative 4x outside. So we get this equation e power negative 4x multiplied with 7x plus x square equal to 0. And because e power negative 4x is not equal to 0, I can get 7x plus x square equal to 0, which is the other factor. Taking x outside, x multiplied with 7 plus 4x equal to 0, and that gives x as 0 or negative 7. To solve this equation graphically, we can graph these two functions. Y1 as 7x multiplied with exponential negative 4x plus x square multiplied with exponential negative 4x, and y2 is taken as 0. Then what we need to do is we need to find the x coordinate of the point of intersection. We select a window something like this: negative 10 to 10 for x and negative 200 to 200 for y. The graph will look like this. So I need to find the two intersections. So we have the solution negative 7. To get the second intersection, I repeat this process. I will get the second intersection at the origin. X equal to 0, y equal to 0. Our solution will be x equal to 0. Objective 5. Compound interest. The compound interest formula is written as a equal to p multiplied with 1 plus r over m to the power mt. Here a is the future value of the investment. P is the initial amount, also called the principal or the present value. R is the annual interest rate as a decimal, and M represents the number of compounding periods per year, and T is the number of years. Here is a compound interest problem. Find the amount to which 1,500 will grow if deposited in a bank at 5.75% interest compounded quarterly for 5 years. We are going to use the compound interest formula here. Notice that interest is compounded quarterly, so M value will be 4 times per year. Substitute the value for P, and the rate is taken as a decimal, 0.0575, corresponding to 5.75%. When we do this calculation, we will get $1,995.55. Notice that when you are entering this in the calculator, you need to put 4 times 5 in a parenthesis. Continuous compound interest. If P dollars are deposited at the rate of interest R, compounded continuously for T years, the future amount in dollars on deposit is A equal to P multiplied with e to the power RT. This is the continuous compounding formula. Example, what amount will an account have after 10 years if $1,500 is invested at an annual rate of 6.75% compounded continuously? Here we need to use the continuous compound interest formula. A equal to P multiplied with e to the power RT. Substituting the values, we will get 2,946.05. One more example, a couple just had a baby. How much should they invest now at 5.3% compounded daily in order to have $60,000 for the child's education 17 years from now? Assume a 365-day year. $60,000 is the amount after 17 years. So we will take the value for A as 60,000. The rate is given and the frequency is 365. We need to calculate the value for P. So when we substitute in the compound interest formula, we will get 60,000 equal to P multiplied with 1 plus 0.053 divided by 365 to the power 365 multiplied with 17. So when we do the calculation, we will get $24,371.39. Notice how we enter this in the calculator.